So our last lecture is on the sustainability issues during the START project. So the speaker will be Dr. Eduardo Santos from TrWshop. So the floor is yours.
Okay, thank you. Well, good afternoon, everyone. Hope everyone is still awake for this last session. I'll try to make it not as heavy as possible. So, first of all, TrWshop, we are a company that is focused very much on environmental engineering, and we are essentially a consultancy company, and we are part of the START project to do mostly life cycle assessment and life cycle costing activities. Here are some of my colleagues. I'm here today, but we have all been part of this work. And so the idea today, a bit of workshop in the sense that we will try to explain a bit how we do the LCA methodology and also the life cycle assessment, but mostly focus on the life cycle assessment. But also try to convene and show a bit of the results that we have been achieving so far within the projects of the START. So first of all, the goals of this workshop are mostly to show how basically the methodology of LCA is conducted, what is the type of data that we usually have to collect and transform in order to achieve the results to assess the environmental performance of the products, and also to go along the steps of LCA methodology development so that you can sort of get acquainted with the steps that we already did. So the majority of those steps are to define the objective and the scope of the LCA, so it's important, or you can do the LCA for different purposes, and I will show in a bit what those purposes can be. Also, very important step to define a functional unit. So it is, the LCA is strongly dependent on the functional unit, and I will go also through that in a bit. How we develop the data inventories, and how we also quantify the environmental impacts, and also how we should interpret and what is the, how important it is to have a life cycle, our whole life cycle perspective of the environmental impacts, and not just single out specific life cycle stages. So just to give you a sort of a helicopter view, so there are many tools that are incorporated within the industrial ecology field, where we can sort of assess the impacts of the environment, but also on the economy of the products and services. But LCA, or life cycle assessment, is sort of the base of those methodologies. They range from sort of micro scale to macro scale within the units and the physical objects that that the methodologies address, and they also vary from environmental aspects to also the economic aspects. Life cycle assessment is very much focused more on the environmental aspects, not so much on the economical side, and that's what we focused here with the START project on the LCA, and also are much more focused on sort of more micro scale, in this case the thermoelectric devices. Also important to know is that there is within LCA different perspectives. So you can have a perspective of life or cradle to gate, so sort of in the sense that you will address the life cycle stages up until the application, or you can also go beyond that and address also the use phases and the end of life phases, and in that sense you would go from cradle to grave. And that perspective, you can use either perspective depending on the objectives and the scope that you want to use the life cycle assessment for. So there are many definitions. Just to highlight that you can find different definitions for life cycle, and also with that said, you can also find different interpretations of what life cycle assessment can be in some cases. But the most important is that it looks or addresses a set of subsequent activities and processes, and you try to account for every input and output of material and energy, radiation, so that you can account and the environmental impacts. Also, because LCA has become sort of a standardized methodology, and sort of become also a tool that is very helpful to do the analysis of the life cycle of the environmental performance of a given product or service. This has also become the attention of ISO, and there are several standards that sort of standardize the methodology. But the most important message here is to say that life cycle assessment cannot be certified, unlike other systems that are certified under the ISO. And most of it has to do with its nature, which is a relative nature. So the results of the life cycle assessment, they are strongly dependent on the goal and also on the scope of the life cycle. So that said, where is mostly useful to use LCA and where it makes no sense to use LCA at all. So usually LCA would be a very good tool to use to compare environmental impacts of different products. So if you are looking to compare different products, that's a very good tool to do so. Also, if you are trying to compare with the same product different alternatives for materials, for the selection of different ways in which those materials can be manufactured, in the way that the product can be also made available to the user, also the end of life phase. Those types of decisions can be supported with the information that comes out from life cycle assessment. So that is typically a good use of the LCA. Also, when you are trying to sort of compare the performance of a product to a benchmark, so to see how does this compare to the best competitor in the market. So that would be also a good use of an LCA methodology. Also to, of course, identify which are the stages that have a bigger impact in terms of the life cycle, so that you can probably focus on those to try and improve the performance of the product. With eco-design, for instance, and also, of course, then with a wider range of applications like the sustainability strategy, or even for marketing purposes and wider, more commercial objectives. Where LCA doesn't make sense to be used, it's when you are comparing things that are not really comparable. So LCA is not or should not be used to compare things that have different functions. So if products may be similar, or even if the consumer is looking at two products but they don't fulfill exactly the same function, it's a bit of a hazard to use LCA, in the sense that it will not be scientifically correct. Also, of course, it's not a tool that should be used for location-dependent solutions. Those are other type of tools that can be used. And also for risk analysis or strategic assessments, it's not the right tool, because it's a very quantitative tool that you are trying to use to have a very objective conclusion. So in the context of the START project, the focus was mainly to do a comparative LCA, of course, to characterize and assess the environmental impacts of the thermoelectric devices that are being developed within the context of the project, and also, of course, because we are introducing a new material, to compare that with the predominant and more commercially available alternatives, which are in this case we chose the lead telluride and the bismuth telluride alternatives, and to compare with those two. Of course, we had to define a functional unit, and here, of course, we are sort of, ideally, we would be comparing with the same functional unit different products that have exactly the same function, but with the same performance. In this case, we were sort of limited in the definition of the functional unit itself, since the product is something, the new product from the START project is something new. And so we, at the moment even, it's not possible to know exactly what the efficiency is going to be, what the use phase will look like, and also the end of life phase. So we had to define a functional unit, which in this case will be to focus on the production of one module of the tetrahedrite thermoelectric device. We addressed a perspective with cradle to gate, so to include the extraction of raw materials, the manufacturing, the production, and also the distribution, but we'll leave out for the moment the use phase and also the end of life phase, since we do not have enough maturity in the project for the product to be able to characterize this in detail. We of course can do some sort of estimations and use the tool to have a whole life cycle perspective comparison to the leading commercial alternatives, sort of to compare full life cycle impact versus full life cycle impact of the different alternatives. But that will be something that will have to be decided over the coming weeks or months, very few weeks or months, in case the full development of the prototypes is not completed. Of course, also the prospect was to use LCA to provide feedback also to the design of the product, so that we can help as much as possible to achieve a sustainable thermoelectric device in the end. I will go through now sort of step by step on the LCA methodology that we have developed and applied in the project, and also with the results we have achieved so far, but also to remind everyone that this is not fully completed, since also some of the steps of the project are still underway. So first of all, of course, to define the goal and scope, and in this context I already referred, of course the objective was to do a comparative life cycle assessment study, and the scope of course was to include all of the life cycle stages, but at the moment limited to the cradle to gate approach. The functional unit I also addressed. Then number 2, inventory. It's a very sort of critical activity, since it's where we collect and prepare all of the data that characterizes the processes involved in the extraction of raw materials, the preparation of those raw materials, the transformation, the production stage, the distribution. So it's sort of the burdensome activity within the project. And I will go a bit in detail ahead on what we did on that stage. Then number 3, of course, impact assessment. So we use a lot of support from softwares that basically apply and develop the methods to do the impact assessment, where we convert basically the physical units in the physical units, so the occurrences, into what is classified as environmental impact. So basically to convert physical units into units of impact, of environmental impacts. And then we do the interpretation of these results. Okay, so now I have the image here as well, it will help me. Okay, so just to give a first guide on how the principles of LCA, which principles exist, and why these are so important. So many of us, of course, have been exposed to environmental indicators for products, even on our daily lives, not necessarily only like big engineering products or services. And the issue very often is we look at that result and it seems that there is no harmful product. So every product is now sustainable, it's eco-friendly, it's the best. So what is the importance of these principles for LCA? LCA is essentially a process. More than the results is a process. And so what makes it different from every other methodology is that you have to follow these principles to make sure that the result then is a robust and scientifically strong result. So in this case, of course, life cycle perspective, you have to take in consideration all of the life cycle stages when doing the accounting of the environmental impacts. So it's very easy if I look into a product and I know if the environmental impacts are associated with the extraction, where the pollution may be happening and contamination of wastewater is going to the rivers. If I exclude that from my perspective of the analysis, and I'm just looking at the production stage where I just have the raw material already prepared, and then I forget totally about the extraction, then maybe my result will be very positive, because that will be sort of a clean process and a clean product. But this is essential in life cycle assessment, to have the whole life cycle perspective. So you cannot allow any shift or changes of the exchanges of the environmental burden to go from one stage to the other. So you have to account everything. That's a very important perspective. Also, environmental focus, of course, to focus on the materials, on the energy, on the environmental relevant impacts. So not other economic and social aspects. They are not they should be addressed, of course, but not necessarily with this tool. Also, it's a relative approach to a functional unit, so it's very important. I can always relay a positive picture if I have a functional unit that serves my interest. So it has to be very well defined, the functional unit, so that I'm comparing the things that should be compared in the right way. Also should be an iterative approach, so it's not something that we just do once. There has to be multiple times to do it in order to make sure that there is quality in the final outcome. Transparency is also a very important step. The main difference, as I said, when looking at a result from an environmental impact of a product or the other, is if I'm able to understand how that result was achieved. And it's essential that the life cycle assessment practitioner does report everything and puts it in a very clear and transparent manner to the one analyzing the result, and that will give confidence on the result. So transparency is also a very important principle. Of course, comprehensiveness to consider all of the attributes and aspects related to the natural environment. So not just to fixate on a given aspect where, of course, maybe our product would shine, but I have to look at the big picture, and so that is also an important point. And finally, to have a scientific approach. So decisions on developing the LCA should be based on natural science, on science, as much as possible. We also know, of course, that it's not always possible, so there are some steps that are unknown, and so as much as possible, use science-based decisions. Even when those are not possible, maybe use methods that can be internationally accepted, and so in the way that every practitioner will use the same method, and even only if it's not possible in any other way, have to use methods that are not scientific, but that should be, of course, avoided as much as possible. So just to run through a bit on the stages. First of all, goal and scope. I know this may sound a bit complex, but the reality is that there are, within the LCA practitioner, there is different types of definitions of goal and scope, and so we should pay attention to these when defining the early goal, when defining the goal and scope. So we will be able to do, or have as alternatives to do an LCA only to do the accounting of the life cycle assessment, so life cycle impacts, maybe for the purpose of knowing the absolute values of the environmental impacts of a given product. But usually what the practitioners want to do is to do LCA as a support to some decision making. And so in that context, you can also have decision making which is sort of large scale. If you are looking at do sectorial strategies, or if you are taking decisions that will affect large systems, or which is the case of applicable to start, we would say, it's that situation A where we basically are using LCA to have a tool that will support us to have decision making at a micro level. So the decision level at deciding what type of materials we can use, where we can use them, so very specific decisions. And so in the context of START, the goal was basically to develop a sustainable thermoelectric device based on tetrahedrite to assess the environmental impacts and compare those with the commercially available alternatives, as I referred. And the scope was to include all of the processes from the extraction of raw materials to the production and distribution stages. As I said, the use phase and the end-of-life phase hopefully will be also incorporated, but at the present time, the focus or the scope is limited to these life cycle stages from raw material extraction to the distribution. Moving on to the step number 2, so inventory analysis. This is, as I said, usually, and we are still running some, in some cases, the inventory always trying to improve as one of the principles of LCA development, which is to be iterative, so improving as much as possible. But this is one of the most burdensome steps because it's where we collect all of the data from in this case, from the partners for the project, to try and characterize the processes that are used to extract the raw materials, to produce the products, to eventually distribute them. And so this is a very burdensome task. Very often what happens is that the partners themselves, and even if this is being applied in a sort of a market-based application, it's very common that even the companies don't know all of their processes and the supply chain and all coming back from that. So it's a process that usually involves a lot of questioning, a lot of asking people and talking to people and asking them for data. And often also happens that people don't have data and should, in theory, go and measure those processes and the materials and produce those data to be able to be used in the life cycle assessment. Of course, we also use, fortunately, there are databases that can help us do that, which already incorporate many of the processes. And even if they are not exactly the same processes that can be attributed to a given life cycle, we can sort of use them and adapt them. And that's what we did very often in this START project for the processes in this scope. And so basically we try to build a process tree and to characterize all of the data, which includes materials and energy which are used and lost in the different stages. And so these are some examples of the types of data that we should be and have been collecting. These are not necessarily from the START project, it's just an example because it's very comprehensive, but it's the type of information that we should be having and have to characterize. So as you can see, there is a lot of data there, and there is a lot of parameters that it's not very often that producers or the activities in general are characterizing. So usually when we are doing LCA, we are sort of asking the stakeholder to generate data. And so it's an additional workload that has to be done. I'll just skip through this because it's types of data that we end up collecting. So energy inputs, raw material inputs, other products and co-products that can be used in the manufacturing stage, for instance, the emissions to air and soil and water. Also, we have to do validation of the data because it's not just a matter of receiving the data and just accepting it as it is. And of course, the data is generally not in the way that we need it to be. So we have to be able to correlate the data with the functional unit or the process that we are trying to characterize. And so this will takes us to a point here which I would like to address, which is very important. That is the issue of allocation. So it's very common that we receive data to characterize a given process, but the reality is that we receive, for instance, the amount of water that is discharged from a whole facility. And the fact is that we are just looking or focusing into a process that is a part of the facility. So it's the facility may generate a lot of products, a lot of outputs, but we are just trying to look to single out one specific output. So we sort of encounter this issue of allocation. And what the practice to do LCA tells us is that we have to do proper allocation. And so first of all, we try, of course, to avoid any of these issues. So as much as possible, if necessary and if possible, try and measure specifically the process that is related with our product, not necessarily with the data that may be available and that is related to our product, but with other products. And as much as possible, try to focus on that. But if not possible, we try to look into the processes more in detail and have to do basically allocation exercise. And so typical examples of where we have allocation issues is to, for instance, I'll just skip to the next slide, sorry. Maybe we have the data for the whole facility and we have also a data for a part of the facility, but not necessarily the part that we would like to. So a possibility maybe is to simply enlarge the scope of the assessment and by difference try to look and find what is the contribution of the process that we are trying to focus on our product. So that is one approach that we can take. Other approach which we did with the START project, for instance, when looking into the impacts or in this case the inventory for the processes of the extraction of the raw materials, we basically had information about the ores and the materials that compose those, or not necessarily the materials, but the components of that ore. And we were trying to look to single out each of the individual materials. And what we find out is that we have the data for the amount of the ore, but we don't have the data for the specific components of the ore. And so there is an issue here. How do we attribute the impacts to, or the characteristics to the components of the ore? And so in this case, we have either mass allocation or, for instance, economic allocation. Mass allocation is typically what we try to use because it's more objective and it's more like scientific, more physical. Economic allocation can also be relevant. Not in this case. For START, we did use mass allocation. But when we are looking maybe at materials that may have small mass, but maybe a very relevant economic importance, usually that can be also a good criteria to use on the allocation so that we can make sure that that material that has a high economic value can be, that high economic value can be translated also into the relevance for the contribution of the environmental impact. So the drive of that environmental impact will be mostly associated to that material, and the other one probably could be waste. And so in this case, it would be also a good option to use the allocation based on the economic weight. So other issue with allocation is, which we haven't found yet in START because we are not using or including the end-of-life phase for the moment, but it's the recycling issue. So this is very typical. When you have a product that will be collected and recovered and processed, and then you will have the materials separated and be returned to the production processes, the question is, who should get the credit from the recycling? Should it be the new product, or should it be the product that originated the waste that is going to be recycled? And so usually we'll find two situations when there is closed loop recycling. where the material coming from the product will be used in the same material or in the same product or in the same type of product, it's sort of almost resolved. But when it's going to be used in a different product, who should get the benefit or the credit from the recycling of the material? So here there is a decision to make, and there is an allocation issue. And usually what the systems do is that they will, depending on the methods, but they will provide the credit to the product that has generated the waste. So for instance, in the situation of the START project, if we are, and hopefully we will be able to do so, to incorporate the end of life stage as well, if the material is able, whichever material and whichever amount can be recycled, that credit from the recycling will be attributed to the TEG tetrahedrite component that is being developing here in the project, and not necessarily to the product that will be using the material. And that is just to show you how this life cycle assessment has conventions. So it's not something that is necessarily scientific and is purely scientific. So again, this is why it's so important to look at life cycle assessment as a process. And as much as that process can be robust, following the principles and being transparent and all of that, and having these decisions being made well visible and also made according to convention of international practitioners, then you are mostly providing a bigger confidence and robustness to your end result. So this was an example of the inventory analysis and the issues that we faced during the development of the life cycle assessment. Also in START, this happened. Then at the impact assessment stage. So there are different ways and steps that we can use to quantify the environmental impacts. I have split it there, those that are sort of mandatory, which you need to have in order to quantify the environmental impacts, and then others that you could say that are optional. But nowadays, this optional part is very much used because it relays the result into a way that is easier to communicate to people. So it helps us a lot in interpretation. So first of all, of course, select the impact categories in the best available models to be quantified. And then in the quantification itself. So identify the environmental interventions that contribute to a given impact category. So this is classification. So basically you will have many possibilities of environmental impact, so they can occur in many categories. And at this stage we have to identify. So we need to classify, to organize, to sort of attribute the environmental manifestations in two categories. Then the second part, which is characterization, it's about quantification. So now we have defined the categories and we have to quantify on each category. So we need units and we need amounts to basically assess how much of the impacts have been generated in a given category. So this is sort of the minimum to do the life cycle impact assessment. Then you have methods that will allow you to have sort of normalization, which is basically to have a unified normalized unit or absence of unit on the result, because you will have many different categories of impacts. Some of them cannot be related with each other, but normalization allows you to sort of relate with each other, because you are sort of normalizing into a reference, which is typically the environmental impacts of one average citizen throughout 1 year. And so you can have each one of us impacts in many categories, and by comparing the impact in each category, for instance, for the TEG module, in each category, you can compare this to the impacts that I had during 1 year on average, and then by looking at that, you can see how the impacts are among the different categories. I will show you in a bit. It's maybe easier shown than just explained. And then there is the topic of aggregation. So usually methods of environmental impacts will have many categories many different categories, like 14, 15, it depends, but it's a lot of impact categories, and it becomes difficult to have a clear picture on what the environmental performance is. If it's because you'll have high results in one categories and very low results in other ones. And so you will need to sort of weigh those categories. And this is a bit of a controversial step, because it's highly depending on the values of people. It's sort of not a direct analysis of technical coefficients, let's say it in this way, but it's really something that asking people if they value more, for instance, their health or the environmental or the loss of biodiversity. So this step with aggregation is also an important step, but if well done, and many methods use and develop this, it's very helpful to reduce the number of categories and have sort of a single score for the environmental impact, which is a good way to communicate. So classification and characterization, I'll just skip this. And this is just an example of the IPCC characterization factors. So it just tells you that the way that the impacts are measured, it's something that is science-based. So in this case is the global warming potential for different substances, and that is correlated, of course, to the CO2 equivalent unit. But it's just to show that the characterization is a science-based step. And with this, I would like to basically to show you how a method for impact assessment is basically built. So we have the inventory. So it's sort of the list and the amounts of inputs and outputs that every process has, energy, materials, and all of that, mass. And those are transformed, so the changes, the outputs from the processes, they correlate with changes in those, with the environmental impact categories. These categories have units that are physical units. So you can, of course, measure if I'm having a trip using my car and it's emitting CO2, you can measure the amount of CO2 that is coming out of the exhaust pipe. And you can also measure how much of that CO2 changes the concentration of CO2 in the atmosphere. So of course it's not direct, but you can, it's possible to make that sort of calculations. So you can have a direct measure of your impact or your inventory, how much you have emitted of CO2, for instance, for climate change, for the emissions of CO2 that then transform themselves into the radiative force changes. But these are typically what we designate as midpoint indicators. So they are sort of problem-oriented. So they measure the changes in the creation of problems, so the increase in CO2 concentration in the atmosphere. But if I'm telling you that, okay, so we are here, everyone is breathing, so we are emitting CO2, so we are increasing the amount of CO2 in the atmosphere by X amount. And the question is that really a problem for myself, or am I, so what is the impact that I'm having with that? So practitioners then had the need, or felt the need to have what is called endpoint indicators, which are more like damage oriented. So these are physical units which you can measure. These are also units that you can measure, but they are based on the consequence. So, for instance, the smog, you can measure how much has been increased, the smog in the atmosphere, for instance, but then you can also measure how much that will affect, for instance, the health. So the human health is here a category which is measured, for instance, in DALI, so it's disability adjusted life years. So it's how many years more you live with a lower quality of life, for instance, because you are unwell, you are having a disease or health problems. And so in that way we transform, or the method allows you to transform the emissions from the tailpipe from the car, into changes into the atmosphere, which is the problem or the cause of the problem, and then to the consequence. So how much that will generate in terms of changes to the human health, or then also to the ecosystem quality, so the change in biodiversity, the loss of species, or also to the resource depletion when we are talking about, for instance, for the consumption of minerals or the use of fossil fuel. Because when we are doing that, we are also changing the concentration available in the mineral crust, and so that will also generate damage. And so these two, to summarize, there are basically midpoint and endpoint methods, and for the start project we try to use both. These are more like objective. This can be a bit of subjective, because the changes from one to the other also can be measured what is a state of health or not health. Part of it can be objective, but it's not like measuring changes in concentration of CO2, because that is not arguable. And so many of the endpoint methods also have subjective basis to it. So we try to avoid them as much as possible. So this is just a figure to sort of explain what I have just said before. So you have, for instance, greenhouse gas emissions. This is a midpoint indicator. You can measure how much this has been emitted. Then this will have consequences in terms of changing the radiative force in the Earth's atmosphere. This will change the temperature and then possibly generate changes in living conditions, and that will sort of affect human health, and then it can be measured as a damage. Sorry. And so I think that has been made clear. So, of course, different indicators, midpoint and endpoint, have different advantages and disadvantages. I'm not going to go through in detail for what is in this slide, but I'll just say that both methods are useful. Typically, midpoint will be less or more objective, so it will be less. There will be less discussion on what the outcomes will be. The damage-oriented methods are maybe a bit more subjective, but they are also more useful in terms of communicating the results to people in general, and also to those that can be that can make use of this environmental information to make decisions. And so this part sort of ended those sort of mandatory steps that we need to have in order to account the environmental impacts and to measure them. The steps that I will go through now is not necessarily mandatory, but they are very useful to communicate results in a more friendly way. So normalization, as I explained a bit before, but just very quickly, is sort of a method that is used to divide the environmental impacts that occur for a product, for instance, and you can use that to split or to divide the results by the average impact that a citizen has during 1 year in that same category. So it's sort of normalized from 0 to 100% or even more, but you would say that 100% is the impact that each of us has in a given category, and that will allow us to compare how much is the environmental impact of a given product compared to my environmental impact as a citizen in 1 year. So it sort of allows you to see the relevance and compare different categories with a dimensional sort of without units. So this is just a summary of that. So it's an important step, and weighting, as I said, is usually a step that is where you have many different categories of impacts, and you can, those are very, there are too many, and sort of sometimes they don't allow you to understand if to have an overall picture of the performance, and so this allows you to correlate the different environmental impact categories. but that is done based on subjective, on opinion making and studies, which are usually involve questionnaires and asking people what they valorize more. And so this is a very controversial step. Many practitioners try to avoid it because it can basically transform a result which has for instance, high impact in categories where people then don't valorize those categories, and you can transform a result which is very bad into a very good result because you are just valorizing categories where the product is performing very well. So in the context of START, we use the receipt method, which is one of the most widely used methods for impact assessment in LCA. As you can see, this method goes from the impact or the inventory. So you will have the inputs and outputs of different substances and for the different processes. It will convert those into impacts in many categories. So it's about, I think, 16 or 17. Well, I cannot count them now, but and then it also goes up to the endpoint indicators, where it converts the problem, the impacts in terms of problems to impacts in terms of damage. And this allows ultimately to have a single score. So it's very common for us when doing LCA to be asked for, oh, how much is the environmental performance of this from 0 to 10 or 0 to 100? And usually people are relaying to the single score. And if you understand now, of course, the whole complexity behind achieving a single score, you can also understand that it's possible to have a single score that it's very high or very low, and it's all very depending from subjective stages and subjective weighing, which we try to avoid as much as possible. So as practitioners, and we did this in the START project, we try to avoid going from midpoint to endpoint. But if going to endpoint, avoid going to single score and maybe keep within these three major categories. It's our sort of approach. In this case, we are looking at the focus that we try to, well, sort of a result. So we did a life cycle assessment for the tetrahedrite modules developed in the START project, and we analyzed the results in the different categories, and we sort of came to the conclusion, and sorry not having the chart here to show you, but we sort of came to the conclusion that these four are the categories that we should focus on. And the reason for it was because the results were very relevant in these categories, and also because these categories were sort of good showcases or good indicators for what we were trying to showcase, which is, for instance, the replacement of toxic materials like lead with a maybe less toxic material like tetrahedrite. So in this case, we focus on fossil resource scarcity, mostly because of the use of also fossil resources for energy, mineral resource scarcity because of the use of minerals, of course, the toxicity, as I referred, for the substitution of toxic materials with less toxic or non-toxic materials, and of course, global warming potential or the emissions, typical, very more famous sort of indicator, so we had to have it. And so these are results that we have achieved so far in the characterization of the life cycle assessment for the START project. So as referred previously, there are two sort of START project modules. So one is using 100% synthetic tetrahedrite, sorry, and the other one is using it's now 35 to the of natural tetrahedrite, but at the moment or when we did this, was 80% and 80% synthetic and 20% natural. But basically to assess the effect of introducing natural tetrahedrite compared to using 100% synthetic. And that compared to the leading alternatives commercially available, so the lead telluride and the bismuth telluride. So as you can see, bismuth telluride in terms of environmental impacts is the worst in all of the 4 categories that we have listed here to show. And then you have lead telluride is in fact less impactful than the START project alternatives in global warming and also in fossil resource scarcity, sorry. But when looking at toxicity and also mineral resource scarcity, because we are using waste or mine waste, this is a big advantage for the START project components. And also toxicity, of course, it's much better than the lead and also than the bismuth. So it's a bit of a trade-off. LCA always ends up a bit like this. There are many categories. There are results that are best and others not as good. It's very rare that we find something like bismuth telluride being the worst in all of the categories, but I think this is a sort of a clear result. But looking at the others, especially lead telluride and the tetrahedrite alternatives from the START project, then you have a compromise here. So there are aspects that you can work with and take advantage of them, like the toxicity and the resource scarcity, but then there are other aspects in the global warming and then the fossil resource scarcity that maybe you can try to look into to improve the performance of the product. And so here are some of the results. Here we are basically comparing the 100% synthetic with the use of the 20% natural tetrahedrite. So differences are very sort of slight. The amount of natural tetrahedrite is also small in this comparison. But what we can see is that the use of natural tetrahedrite is not, well, first of all, sorry, the main impact is coming from alumina plates on the global warming and also on the fossil fuel or fossil resource scarcity. And regarding the toxicity, the TH legs are they perform very well here. And so the main performance or negative impact will be coming from the use of other minerals than TH. And then here for mineral resource scarcity, it's also the legs, so the use of the minerals that is having an impact on this category. So what these results tells us is that there is not a clear picture that the tetrahedrite product can be a winner in all categories. So there is compromise to be made, but there are some aspects where it can perform or outperform the other competitors, and we should focus on those aspects and try to enhance them. So this is, and also that the use of synthetic is in general an improvement for the purpose of, for instance, global warming, and also for fossil resource scarcity, so to reduce the amount of energy that is being used in the extraction and the production. But it has also its downside in terms of mineral resource scarcity. So it's always a bit of a trade-off that we have to take a look into. So, I mean, interpretation of results is a step that we will go through when we have the final results for the START project. So I will not be going into more details here, but it's just a necessary step where we basically try to draw the conclusions from the results and use those results as best as possible to improve the product. So just a final note on LCA before I just go into the final slides regarding life cycle costing. But just to let you know that as part not necessarily of this project, of the START project, but other projects where TrWshop has been involved. 4 years ago when we started this START project, we were already looking into ways to sort of streamline the life cycle assessment methodology and the process to make it sort of quicker and not so dependent on sort of labor to get to the data, which is it's a big bottleneck for the process, and it's also it makes the quality of the final result very depending on the availability of data to characterize the processes. And so we have been working on this in other projects, but also looking into the START case study, how to introduce AI tools basically to improve on the collection of data, so for the inventory. And now there has been big developments, or there are being big developments in tools that can help reach a bigger amount of data and also to take care of that data. And so that is an important tool to develop for the future, and also for the impact assessment. So there are new methods that can use and benefit from the extensive amount of data that can be used, as long as it can be shared, of course. And this is an area of research that will be developed and enhance the applicability of LCA over the next few years. So just to give you a brief note on that research line, which is going to be an important step in LCA. So just to go quickly in life cycle costing, let me just look at the time, so okay. But I will not go in very much huge detail, because here we are still a bit, results are preliminary and still in development. But here the idea was basically to calculate and assess the costs for the whole life cycle of the tetrahedrite components developed in the project, and also to compare them again with competing commercial alternatives. So the objectives of LCC are those. We have used the same functional unit, and that's the way it should be, as the life cycle assessment, and it's also a good, efficient way to do it when we are doing inventory and characterizing the processes that are used to extract the materials and produce and all of that, that we also do the characterization for the economic data. So that's what we try to do for the START project. And so we basically, the functional unit, the objective and the scope is very similar to the LCA, but it's of course focused on the economic aspects. And we focus also on the characterization of the costs of production, the costs of the raw materials, and the energy that is consumed, and the cost of that energy. So we did all of that accounting, with the exception of the use phase and the end of life, because as I said before, they are out of scope for the moment. And so I just wanted to relate to you, to show you the results so far, which are preliminary in terms of the cost assessment. So we are comparing the START Thermoelectric's component with, again, the lead telluride and the bismuth telluride alternatives, similar alternatives that can fulfill the same functional unit. So, and what we are finding out at the moment is that the bismuth telluride are here maybe a bit on the more expensive side. The lead telluride, for this application that we are comparing with the START thermoelectric device, they are the more competitive ones. The START has shown the costs with raw material extraction and of course transportation. It's not so much the relevant one there, but in the same vicinity as the lead telluride, while the production and assembly are very much still on the expensive side. But what the results, and again I stress that these are not final results, but what the results can show us at the moment, and we of course not included the use phase, which should be a productive phase in terms of cost, so it should generate at least avoidance of costs for the user, and we should take this in consideration as well. Any energy that is recovered and produced with the thermoelectrical devices, it's energy that the energy consumer will avoid having to buy. So this should be accounted, again, the allocation problem, but should be accounted as a benefit from the use of these thermoelectric devices. And also the end of life, we have to account that what the costs can be for processing, collection, all of that, but maybe some revenue possibly coming from selling the materials to be recycled. But what we can say is that the prospect of the costs of the start thermoelectric devices is that it should be in the range of what the costs of the current commercial alternatives are. So we should be in the range and be able to offer, at least in terms of price. Of course, there has to be a big discussion in terms of efficiency, but in terms of price or cost, we should be in the same range. And just to close, of course, the life cycle assessment has many advantages and disadvantages. Main advantages will allow us, of course, to have an idea on the costs and what this can mean for the development of a business strategy, which is, of course, also a part of the START project, of one of the work packages, and is also a good way to understand where the costs, where we are or can be improving in terms of cost efficiency compared to the competitors, comparing the different life cycle stages. So where we are more cost efficient or where we are less, and have to focus on that to improve the costs in that stage. And of course, there are many disadvantages. Is of course time consuming, and there is a lot of uncertainty associated to it, especially when doing this exercise for the START project, because many of it is not yet at full scale or even at industrial scale. So a lot of it is uncertain. So okay, thank you.
Thank you very much, Eduardo. I don't know if is there any question? Yes.
I'm a bit surprised about the positive outcome for lead telluride, to be honest. In both your assessments, the lead telluride seemed to be much more positive than the bismuth telluride. I would expect completely the opposite. In both, also the cost picture that you just sketched. So environmentally, it showed a better than bismuth telluride, and here in the cost as well.
Yeah.
Does that make sense?
I mean, in terms of comparing one with the other, so lead and bismuth, has shown to be less performing. But if we look at and I can go back, I don't know if it's available. No. Can you put the slides? Yeah. So I'll just go back. This one. So as you can see, well, at least in some of the categories like toxicity and resource scarcity, well, they are sort of similar. Maybe a bit here, the 10 times, so it's a bit different. But in global warming and fossil fuel resource scarcity. So this has very much to do with energy consumption, especially during the process of production and extraction of raw materials. And also this is to do with emissions. So this is something that we have sort of characterized and analyzed. And we have compared it with literature. And it sort of aligns with what we are. So the results are not, they may be a bit unexpected, but it's aligned with what we have looked into the literature. So I understand maybe the part of toxicity that we would expect maybe lead to be more toxic, or at least much more toxic than what the tetrahedrite is showing. But so maybe the choice of colors is maybe getting a bit a positive idea, but actually lead is worse than tetrahedrite, but still is showing up a bit better than bismuth. So here maybe a point of questioning. But from what we have made in terms of analysis is sort of aligned with what the literature is also showing. Yeah.
It is what it is. I mean,
okay. I mean, that's what the life cycle assessment is for. Trying to bring, yeah.
In the production, you considered that it is already a mass production in the case of tetrahedrites or not? Because in case of bismuth telluride and lead telluride, it's already settled.
Yeah,
In the case of tetrahedrite, not so much. And
yeah.
what did you consider?
Yeah. So as I said, this exercise, it's we try to put the so of course the same functional unit, and we try to put things in perspective. So when we are trying to compare these results, we have data regarding the manufacturing of lead telluride and bismuth telluride, because that is very widely available. Not so much for tetrahedrite. So what we do is that we sort of extrapolate many of these factors to use it and incorporate it as part of the tetrahedrite. So in this case, what we are assuming is that the expectancy of tetrahedrite becoming sort of a mass production, but it's not necessarily yet there. So we have this in account in the model.
Okay, thank you.
So if there are not any more questions, we'll go for the conclusion. Thank you very much, Eduardo.
Thank you.
I will ask Philip, as the coordinator of the project, to say something as the conclusion of the webinar.
I will be very briefly. So today we cover many different topics related with the thermoelectric technology. I hope you found them useful for you, and I want to acknowledge all the speakers and also for your presence here, also for who are online, and I also to acknowledge Amit and Bruno. They also deserve our applause, and also for the technician. Okay, thank you.
Thank you very much. Just one few words before you leave. We just prepared some certificate of attendance. You can find them on the table in the room and in the exit room. We will send you a feedback survey maybe next week. I will appreciate if you can fill it. And this was the last training workshop we had for the START project in, let's say, its mother town, hometown. Yeah. Our next event will be in Brussels in May, together with the EIT Raw Materials event. And yeah, I think that's all. We will have maybe for the people who will stay for the Sustanet meeting tomorrow, maybe we will have a short discussion after everybody leaves. So I will thank you all the attendees, both our online and in-person participants, and wish you very nice evening and weekend, and safe journey back home. Thank you very much.